So, hi everybody, I'm Lisa Lippincott, and I'm here to talk about why loops end. Now, sometimes my titles are a little obscure. I think this one is fairly straightforward. We write loops in our programs, we execute those loops. Sometimes those loops come to an end, sometimes they come to an end for a reason. I'm going to talk about those reasons. So, jumping right in, why loops end, reason number one, the heat death of the universe. So, computation, like so many other activities, increases the entropy of the universe. It converts free energy, which can do work, into thermal energy, which cannot. This process is irreversible. Left unchecked, any loop will consume the free energy of the universe to the point where not even a single instruction can be executed. So, loops do end. So, let's try out that reason in the context of code review. Here we have our interlocutor asking us about a particular loop. And our answer is, yes, it's going to end because all of the free energy in the universe is going to be used up, and when it's used up, the loop will be over. And this turns out to not be a satisfying reason. But you know, you ask the wrong question, sometimes you get an unsatisfying answer. Really, this guy wanted to ask some more specific question about why the loop will end. So let's rephrase. Will it end for some non-cosmological reason? Well, that's still very broad, and in a certain sense, that kind of means it ends for a reason outside the cosmos. But it's at least getting at an idea that the problem with the heat death of the universe is that it is big and far away. It is a long way from our program, and we want the reason to be close to us, to be in our program. So, we'll try to be much more specific. Will this loop end for some reason that is expressed on every code path that enters the loop, is complete before any part of the loop is repeated, and is not separated from the loop by a function interface? That is a very specific set of criteria. It says the loop has to be expressed in the program in the right part of the program. It has to be expressed in a certain sense near the loop. Now, I did refer to function interfaces, and by function interface, I mean a specific thing that I'm going to be introducing a syntax for. Here is the syntax. A function interface in this notation looks like a function body that sits between the caller and the function implementation. And in this body is split in half by this implementation statement. That's where the implementation of the function happens. The part before expresses things that the caller is responsible for. The part after expresses things that the implementation is responsible for. So preconditions go up above, post-conditions go below. And preconditions are evaluated before the implementation. Post-conditions are executed after the implementation. So that's our notation for a function interface. And we're going to use function interfaces to divide our program into neighborhoods. Function interfaces are the boundaries of neighborhoods. They're where one neighborhood meets another. And we are going to insist that our reasons for loops ending have to be in the same neighborhood as the loop. So let's go back to our conversation. We'll call that a local reason. And we ask, does the loop end for some local reason? And well, you might think, let's write a comment into the code right before the loop that explains why it ends. And that is a good start, perhaps. But I'm going to say that doesn't satisfy me. Or rather, I'm going to introduce you to our robot pal. And I'm going to have our robot pal here assist in code review. And this robot reads the code like a compiler would, ignoring the comments, and still needs to understand our reasoning. It still needs to understand the reason why the loop ends. And of course, by robot, I really mean algorithm. And by algorithm, I want to emphasize that I do not mean one of these newfangled cat recognizers. I mean a good old-fashioned algorithm that people write and debug and agree on the correctness of and standardize, so that we can all agree when somebody has clearly expressed a reason why the loop ends in their code. So that's our problem statement for today. We are going to try and express the reasons why loops end in the structure of our executable code so clearly that a robot, that an algorithm, can read those reasons and check that our reasoning makes sense, that our reasoning actually leads to the conclusion that the loop will end. So the next question is, what does the robot look for when it reads our code? And it looks for three things. It looks for periods of stability during which the state of an object doesn't change. So stability, one of our fundamental three things. I'm going to make an aside here. There's been a lot of talk this week about memory safety. Getting stability right is what gives you memory safety. Stability is about that. Next thing the robot looks for is substitutability. Times when two different objects are going to have the same value. And this is what makes values transportable to a different object. It lets us say it is sensible to even say that two objects have the same value. And the final thing the robot looks for is repetition. When an operation is so like a previous operation in the neighborhood that it must produce a similar result. So those are our three things. Like I said, there's been a ton of talk about memory safety this week, so maybe I should be giving a talk on stability. But in fact, the star of the show today is repetition. Because repetition is really both the important factor of how we use function interfaces, and it is vital to knowing how loops end. So, how does the robot find out about stability, substitutability, and repetition? Function interfaces tell the robot about all of these things. So that's how smart our robot is going to be. It's going to be looking for these things. It's going to be reading code in the neighborhood, not beyond any function interfaces, just within our neighborhood. And it's going to be looking for these three things and what the function interfaces say about the state of the program. Yes?
What does the robot understand by similar?
We'll get to that.
Okay.
So let's take a look at some very simple loops to start with. Here are two loops. And we'll ask our robot about it. Robot has differing opinions about these two loops. We want our robot to approve of the first loop. Say, yes, robot understands why this loop ends. We don't want the robot to say the same of the second loop. So what's the difference between these two loops? Well, it's the difference between true and false. And it's important in this context to understand true and false not as values. You're probably used to thinking of them as values. But a better way to think of them is as operations. True and false are operations that produce, that initialize an object and give you that object. And in this case, when we think of them as operations, we can talk about their interfaces. And here are interfaces for false and true. And you will notice that they're mostly the same, but there's a little difference between the two. This if statement expresses the difference between false and true. The difference in this if statement expresses the difference between false and true. So let's take a moment to read through that. If we look at the interface for false, there are no preconditions. We started with the implementation statement. The caller is responsible for nothing. We come down to this line here, transfer stability. In previous talks, I called it claim right. I decided that was obscure, so I'm going to go with transfer stability today. This is saying that this function gives the caller a right, a transferable promise, to the stability of the result object it creates. So the caller will know, so our robot sees this and knows that a period of stability has started. Discern is about repetition. When I say discern in a post condition, and when I say it after the implementation statement, I mean that this is something that will be the same when you repeat the operation. So this line is saying that every use of false will produce the same value for result. And then finally, we have down here, there's this call to unreachable. And of course, calling unreachable, if it actually happened, would produce undefined behavior. But it's important to know that undefined behavior in somebody else's post condition is not your fault. It is somebody else's problem to make sure that unreachable doesn't ever happen. And in this case, it will be the compiler / computer / electrical system or whatever is making the computation go forward. The branch is supposed to go the other way. So with that, we can come back to our program and see that the branch in our loop repeats the branch in the interface of the function. Or maybe, well, the evaluation goes the other way around because before we branch, it branched. But, oh yeah, our branch repeats its branch. Anyway, when one branch repeats another, it has to go the same direction. If they don't, something is wrong with your compiler / computer / whatever. Something is wrong outside your function if these go different directions. So here, this shows that this loop ends unless something that wasn't our fault happened. And that's our first proof that a loop ends. We can make it a little harder. Here's another very simple loop. While 0 is not equal to 0. And you'll see that the robot approves of this one. And you would think, well, the robot knows math, so it can see that 0 is not equal to 0. Not exactly. We don't want to teach our robot math. Math is complicated. We teach our robot to read interfaces. But we can make interfaces that help the robot out. So let's take a look at the interface for not equal. And it starts like this. That's sort of the boilerplate for a simple interface. I'll walk you through it, even though it's mostly the boring part. So here, this extend stability says the caller is responsible for the stability of these two parameters for the duration of the operation. That's its promise to the implementation. And then down below, we have transfer stability. The implementation gives the caller a right to the stability of the result. So the caller ends up with more stability afterwards because there's another object. Discern is, again, about repeatability. So this is saying that when the operation is repeated with the same parameter values, and that's what we mean by repeating the operation, repeating it with the same discernible values. So up above, we're saying, what does it mean to repeat the operation? A and B have the same values as before. And below, we're saying we'll get the same result in that case. So below, we're giving the consequence of repeating this operation. We get the same result object, or we get a result object with the same value. But we want to add like helpful stuff in here, like saying that A not equal A would have been false. So if the parameters match, you would see that the answer is false. That's not something we can just write in there blithely, though, because that would make the whole interface recursive. It's actually just generally a bad idea for an interface to re-enter itself before, without going through the implementation. Ordinary recursion, go through the implementation. So we're going to have to use a trick to not say it that way. And there is a fairly straightforward trick, which is we're going to create a second function. And instead of saying that this function would produce false, we say that function would produce false. And this function always produces the same result as that function. So the robot can follow this. It is not that tricky. You just have more stuff. And I've been using this trick for years. I'm kind of tired of it. It is wordy, it is wasteful. We didn't really want a second function. What we really wanted was a second layer to the interface. We wanted a sort of minimal interface that we can use when we need to avoid recursion or other complexity. And then an outer interface that is helpful and provides all sorts of useful things for most callers. And let most callers just go to the outer interface, but in special cases, we'll go to the inner interface. So today, I'm trying out a new syntax for that. I'm going to rearrange this code and get rid of a decent chunk of it and say we have an interface and we have a primitive interface. And from the main interface, we just go into the primitive interface. And we have this declaration using primitive that tells us in this, in the following code, use that minimal interface and we avoid the recursion. So just a similar trick, but we didn't have to do a whole new function. We just did a second interface, a second layer to the interface, really. We can make this a little bit better by saying, if we were calling ourselves, we really meant to go through the primitive interface. We can make it the default in that case. So direct, just straight into our own interface never happens. Always go to the primitive interface. And this is still a bit more wordy than I like. We can shove that in there, be a little more explicit that it's just two layers of the same thing. And there we have a way to put this helpful stuff at the end, out in the outer interface and still be able to call our function from within it. Enter our implementation from within it. I will go one better here, though. This stuff up here, the caller promises the stability of const parameters. The parameter values are what you have to repeat the function. You get the stability of the result. The result value matters. That's all very boilerplate. And really, we could have guessed that just by reading that reading the function declaration. So I'm going to say that while this isn't universal, in a lot of cases, we can just say, yeah, that's the default. We'll just use it. So now we've got a lot of room. I see a hand.
Yeah, so would you have this split to avoid the recursion? You have the interface called the primitive interface, and a couple of slides ago, they looked almost identical, with the caveat that the primitive interface didn't have the extra claims at the end, right? Because that would be the recursion.
Mm-hmm. So
does it, like, how does, I guess the primitive interface has less information, so how does that get inferred in the interface?
So the the primitive interface becomes a portion of the main interface. That's why you can nest them like that. So you can't do the helpful interface without going through the primitive interface. Hope that helped. Oh, I see another hand.
You want to avoid the complications of one operator calling another, of doing the not of the equals operator?
So the question is, do I want to avoid saying that, yes, this is just the not of the equals operator? I wanted to avoid talking about not today. I mean, maybe we would write it a little differently in practice, but I didn't want to get into a lot of interfaces for bool. And that's really why some of these things are written the way they are. It lets me show fewer interfaces today. So I will say, now that we've made it simple, we actually have a lot of room on the slide. We can put all sorts of helpful stuff about not equal here. We can say that B not equal A would have given the same result. We can actually, here, put in a branch on the result. Not something I generally recommend. Putting if statements in your interfaces, generally poor design. If you put it in your post condition, it kind of forces your caller to also branch on your result to find out what you really meant. On the other hand, how often do you call not equal and not branch on the result? So I'm going to say, for comparisons, I'll go ahead and put in an if statement. And here, if the result is true, we can say a lot of things. A equals B would be false. We can say that A less than B would produce the same result as A less than or equal to B. A greater than B would produce the same result as A greater than or equal to B. Otherwise, we could say, yeah, if this returns false, then A equals B is going to be true. And of course, A equals B would say a bunch of things about A being substitutable for B. So there is a helpful interface that tells you useful facts about not equal. And one of those useful facts can be picked up by our robot because it's being repeated. A portion of it is being repeated in the loop condition. The robot can see that this loop condition is false because it's repeating that claim. And we already know false makes the loop end. So this is why the robot can see this loop ends. Okay, we'll make the loop a little tougher. Here we go. I'm going to break this out and make it a counting loop from 0 to 0. This really isn't much different. The robot just had to understand stability to get this. It understands that when we initialize I with 0, we get a write to the stability. It hasn't seen any interface where we give up that write when it comes to the loop condition. So it can see that the left-hand side is still what it used to be. We know that these two executions of 0 are going to produce the same value. The interface for 0 would tell us that. So this, just like before, is going to match the thing in not equal that says not equal returns false. And the robot can just read through the code and see, yeah, there's a reason why that loop ends, and it's just here in the neighborhood. Okay, we'll make it a little worse. Counting to 1. Apparently the robot still approves. There must be something it's reading that says this loop is going to end. What could it be? Well, now it's having to read the interface for increment. And okay, there's a bunch of stuff there. You see the interface for increment is a point where we transfer away the stability of this object. But we get new stability back after the increment. There's just a gap. But the interesting thing is the first line and last line of the interface. So we calculate what the next value is, a plus 1. And down in the post conditions, we say, yeah, the result you get is actually the thing we predicted. So the robot can see that this increment is going to produce the same value as 0 plus 1. What does the robot know about 0 plus 1? Well, it's going to read the interface for plus because that was called. And something we're surely going to put in the helpful interface for plus is that when you add 0 to something, you get the other thing. So these two interfaces together, just walking through them, our robot sees enough by just looking at repetition, stability, or substitutability, and stability to say, yeah, this loop is going to end on its after its first iteration. Okay, we could make it a little easier to see that reason, though. They're starting to get a little hard for humans to see. So if we want to make it easier for humans to see, we'll put in another thing for the robot to check right up front. The robot can check that 1 is equal to 0 plus 1. And it's just doing that same thing a little earlier now. So moving along, 2. What about 2? Can the robot see that 2 is 0 plus 1 plus 1? I thought it wouldn't be able to when I started putting this lecture together. I was like, okay, this is the point where I'll do something different. And then I checked. I went through all the interfaces that this would go through, and it turns out one of them gives it away here. Because 2 is one of those operations that initializes an object, and it has an interface. And the way we have to write that interface in C++ is as a template specialization. We have to specialize a templated operator quotes to give the interface for single-digit numbers. So all of the single digits have a specialization, and well, you're going to put in the most important thing to say about 2, which is that it's the next number after 1. So surely we will put that in the interface, and the robot will see that this loop ends. We can walk through 3 through 9 also. We have to do the same thing for every single-digit number. Turns out, because we're going to use it in the general case, we have to provide a specialization for 10 also, for 1, 0. So we still are providing enough for the robot to figure out that the loop ends when we get to 10. 11, we're finally in the general case of this template. But turns out the robot sees enough in this one to figure out that 11 is the next number after 10, because the interface is going to say, well, it's 10 times the first digit plus the second digit. And the first digit is 1, and the interface for operator star is going to tell the robot how to multiply by 1. So the robot can definitely figure this one out too. At 12, the pattern breaks, because the interface for 12 tells the robot that 12 is 10 plus 2. Nobody tells the robot that 12 is 11 plus 1. So I know I'm sort of putting words in the interfaces of the future's mouth here, but when I write them out as honestly as I can, this is where things break down. So what do we do here? We know that loop ends. We just haven't adequately explained it to our robot. We haven't made a local reason embedded in the code, in the structure of the code. Now, there's a simple change we can do, which is change that claim to a static assert. Our robot isn't checking static assertions. That's the compiler's problem. If the static assertion fails, the program is ill-formed. No one should be running an ill-formed program. So if somebody runs this despite the static assertion failing, it's not your fault. And so our robot will just assume that anything in a static assertion works. So it knows it can do that long computation and end up at 12. And that is good enough to see that, yeah, after 12 iterations, the while loop is going to hit a true condition, and we're definitely exiting. There is the question of, well, the robot is getting a little tenacious here. Why is the robot going on for 12 iterations before giving up? But we'll get to that. But first, let's look at the harder program. No static assertion is going to explain why this loop ends. This one is just harder, because we don't know where we're starting, we don't know where we're ending, but I think all of you will agree that, yeah, that loop's going to end. We need a little bit more theory to understand why this loop ends. And I went through my bookshelf and looked for a nice, concise description of the bit of theory we need. And the best I came up with was this quote from Bertrand Meyer, which honestly, I think says something is wrong with my bookshelf. This is really much wordier than what I was looking for, but here we go. A variant is an integer expression whose value is non-negative after loop initialization and is decreased by at least 1 for every execution of the loop body when the exit condition is not satisfied, but never becomes negative. That's a mouthful. That is Bertrand Meyer, Object-Oriented Software Construction, writing in 1988, 35 years ago. He is writing about Eiffel. Eiffel had a mechanism for specifying loop variants in this manner to help you ensure that your loops will end. Eiffel is a very influential language. We're not using this. Almost no languages are doing this. Some are, but not as many as one might hope after 35 years. And I think it's because there is something not mathematically wrong with this, but something that's wrong with this in terms of usability. I think that this is a hard way to get people to think about their programs. But we're going to go with it. I am going to clean it up into something a little more pithy. A loop variant is a non-negative integer expression decreased by execution of the loop body. Fewer words, I think it says about the same thing. Now that non-negative integer business, what we really means is a natural number. I'm sure he said non-negative integer because Eiffel didn't have a natural number type, but did have a type called integer, and that's what was going on. So we can clean that up a little bit, but there is something mathematically wrong. Yes?
You include 0 as a natural number.
0 is a natural number. That's definitional.
But if it starts at 0, is initialized at 0, and then is decreased by the execution of the body.
That means you didn't actually, that you can't decrease it, you would have undefined behavior. So, if you start at 0, you're not executing the loop body. Anyway, so there is something mathematically wrong here. If you ask a logician what the right type is, it's not natural number. There's a whole lot of math around this. The right answer is an ordinal. There is a reason why Bertrand Meyer did not want to use ordinals. Ordinals are really difficult for computers. And the problem is there's too many of them. I would say there's an infinite number of ordinals, but that would be wrong. There is no infinite number large enough to express how many ordinals there are. There are a lot of ordinals. So we have trouble representing ordinals in our computers because actual types in our computers have a finite number of values. You cannot construct a type that has an infinite number of values. So we can't use ordinals. But we also can't really use natural numbers. We don't have natural number types. We don't have integer types. We have types we call integer or natural numbers sometimes, but we don't actually have them. All of our types have a finite number of values. The natural numbers, the integers, have an infinite number of values. So mostly people just ignore this, but I think this is an important point. We're sort of off on the wrong foot already as soon as we try to express this in something that has a type in our computer. So let's reduce this little. A loop variant is something decreased by execution of the loop body. I lost something there, though. This is true, but it's not sufficient. There's another part of it that has to do with being a natural number or an ordinal, which is what mathematicians call well-foundedness. The fact that if you keep decreasing it, eventually it runs out. You can't decrease it forever. So we can try to get that in. A loop variant is something consumed by execution of the loop body in a way that leads to its exhaustion. And that, I think, is a general thing. I'll say it again. I'll clean it up. A loop variant is something consumed by execution of the loop body in a way that leads to its exhaustion. Left unchecked, the loop will exhaust some resource. This actually sounds a little familiar. Where have we heard this before? Free energy is the cosmological loop variant. Free energy is a loop variant that applies to all loops. It is more cosmological than local, so it's not the reason we're looking for, but it's a loop variant. So, rephrasing, if the iterations of a loop consume some resource in a way that leads to its exhaustion, the loop must end. Now, I'll be clear here. Every iteration must consume some minimal amount of the resource, and it is the iterations combined, if left unchecked, that lead to exhaustion. We don't actually have to run the loop that far if something else gets us out of the loop. But if the iterations of a loop consume some resource in a way that leads to its exhaustion, the loop must end. Now, how can we apply that to a program that where we understand why the loop ends? We understand this one. What thing could we be consuming here? Well, if you're focused on numbers, you say, we're consuming 12. We start with 12. Every time we are going through the loop, we consume 1. Eventually, we get down to 0 and we can consume no more. So the loop must end at that point. But that's if you're focused on numbers. That's how loop variants worked for Bertrand Meyer. What if you're not focused on numbers? Then you ask, 12 what? What are there 12 of in this example that we are consuming to get to the end of the loop? And the answer is, there are 12 additions in our past, 12 operations that happened in our neighborhood. And each time we are repeating one of them, and the next time through the loop we'll repeat one that's later. And our robot can see, yes, we're repeating a sequence of events that happened before, and it can say, as long as we're doing that, I will stick with it and watch where it goes. And when it gets to 12, after 12 increments, it says, oh, at this point, the loop condition must be false because we asserted that, because it's done the math at this point. Or because it has matched the assertion. It didn't do the math. It matched the entire assertion at that point, and it says, now we are at the place where not equal will return false. So being more specific, I already hit that slide. Okay, being more specific. If the iterations of a loop repeat a sequence of events that happened before the loop, the loop must end. And again, elaborating on that, each iteration must repeat something that happened before the loop. We're going to require that they repeat them in order. If we point to, here's the last thing we marked off our list, the next thing we mark off our list will be further down our history. So we are consuming our history. And we know that the number of local events in our history is finite. We could have counted them. We could have produced a number, a natural number, to use as our loop variant. But that would be more complicated. We're going to skip all that. And if you're wondering what happened to ordinals, there is actually an ordinal that characterizes the entire collection of paths leading up to our loop. And by picking a particular path to get to our loop, we are picking a way to count down from that ordinal. But we're going to skip all that. We're just going to focus on we're repeating events from our past. And as long as we know that every iteration of the loop repeats an event from our past, we will know the loop has to end, because we will run out of events to repeat. So, how do we do this? Where do we get the events from our past? Well, there's an easy way and a hard way. The easy way is we call a function that gives us a whole lot of events to repeat. And this, honestly, this is the cheap thing. This is make somebody else do the hard work. This is the 99% case. This is what you would really use almost always in practice to say that your loop ends, because, when you think about it, there really aren't that many reasons. When I sort of categorized all the loops I could think of, I came up with a couple dozen, and I probably missed some. But there just aren't that many. There can be a library that expresses all the common things. And so we'll just call into some function whose interface provides us with enough events. And in this case, I will call the function the counting theorem, because I hate the name iota theorem. But, and what this is going to do is produce a bunch of events in its postcondition for us to repeat. Now, this is a theorem. A theorem is a special kind of function. The difference is this line claim implementation. That's just an indication that you can think of the implementation as one big assertion. And it's an assertion that shows us how to connect the preconditions to the postconditions. And the reason we want to mark this off as a special kind of function is that it's not a function that does something. It's a function we can run and test our reasoning. But if we want to run our program quickly, then once we become confident in our theorems, we can skip them the same way that we can turn off assertions or turn off interfaces to make things go quickly. So it is code that can be dispensed with for speed. Anyway, what happens when we count this? Well, first we have to meet the preconditions. How do we know we met the precondition on that function? Well, it matched our if statement. We know our if statement returned true if we, by the point at the point where we call this, we know our if statement went in the true direction. That claim is going to go in the true direction. It succeeds. So we get the post condition really for free. The loop over there in the post condition, that's somebody else's problem for the moment. But that loop we know ends. Our loop, everything in our loop is just repeating something in that post condition. So because the loop in the post condition ended, ours also ends, because it's just repeating the same iteration. In fact, here it will end in sync with that loop, but that's not actually an important property. It's that loop ends, therefore this loop ends. Just because our loop is repeating events that happened in its past. And I'm not saying that these are necessarily the events that the robot will match up. It will in this case. But definitely we are repeating events in our past, the loop ends. So there's proof in the more general case. Yes?
Why do we know that this loop ends? It's just because it's a post condition, so we can assume that a loop in a post condition.
Yes, making that other loop end, we don't know it ends, but making that loop end, the loop in the post condition end, is not our problem, somebody else's problem. And now I'm going to change contexts and make it our problem. How do we implement the counting theorem? How do we prove it? Because the implementation of a theorem is a proof. What can we write here to convince the robot that reads the counting theorem that the loop will end? And I want to say things are going to get a little tricky. I'm going to say there is an important fact about life that I am reminded of in putting together this talk. Familiar is not the same as trivial. Counting is familiar, and that does not make counting trivial. In fact, of all the loops I've tried, counting is one of the harder ones. So when you look at this, think, yeah, this is a kind of expert level proof. I think it's not as hard as the next permutation loop. That one was pretty tough. But it's up there. So we are going to need to know some things about integers in order to do our counting proof. First thing to know about an integer is that we can measure an integral type with a measurement called width. It is measured in bits. An integer is so many bits wide. Integral type may or may not have a sign bit as its high bit. I'm going to take those two parameters for an integral type and combine them into a structure I call the integer kind. So that's just, is it signed? What is the width? And there are three special kinds that we're going to be seeing. The bitless kind, which is there are no bits, the only value is 0. The unsigned bit kind, where there are two values, 0 and 1. And the signed bit kind, where there are also two values, which are -1 and 0. Those are the three special cases. So that's integer kinds. What are we going to do with that? Well, we're actually going to break down our integers into smaller kinds. And there's a particular boundary I'm going to break it on where the low order bits are the largest power of 2 less than the full width. So low order bits is a big power of 2, is a power of 2, and the high order bits are no wider than the low order bits. And of course, I'm not going to stop there. I'm going to do this repeatedly until we break things down into single bits. And single bits we can convert to Boolean. And then we can branch on the Booleans. And if you think about that a minute, that's going to have a ton of execution paths. There's a lot of execution paths through here, we're going to overwhelm our robot if we're not careful. So instead of having one robot do the whole thing, I'm going to break this into neighborhoods and have a robot for each neighborhood. We're going to do this one step at a time so that none of our robots see very many branches, and that won't overwhelm them. And of course, we don't have to repeat them. We really only need this many, one of each kind of, one neighborhood for each kind we go through. So that's our plan. We do need an intermediate type for this. The intermediate type I'm going to be using, I call widening. The reason is in another talk. The name is not important today, but I'm going to stick with it here. And it has two useful properties for us today. One is it comes in whatever kind we want. If we want a 3-bit integer, we can ask for a 3-bit widening. We can ask for a 3-bit widening, signed or unsigned. The other thing is it doesn't promote to int, because we'll never get anywhere if we keep going back to int. So this is not a proper C++ integral type because it doesn't do integral promotion. It doesn't do usual arithmetic conversions. It is its own thing, but it is still something that we are using to represent integral numbers. I'm also going to make some aliases there so that I don't have to type out complicated template stuff. Bitless is a widening of the bitless kind. Unsigned bit is a widening of the unsigned bit kind. Signed bit is a widening of the signed bit kind. So just handy names for things. We need operations for breaking stuff down. 2 widening split bits, 2 bool. You understand what those are from the picture before. We're just converting, we're converting or splitting to get down to single bits. That would be enough, but it's actually convenient to have the reverse operations too, so I will put them in. 2-bit join bits, 2 integral are our reverse operations. And if you want to see more stuff using these types, and for that matter, find out why I called them widening, you can see the talk I gave last year called Principia Mathematica, the Foundations of Arithmetic in C++. More good stuff there. So we've got that. We do need to know some things about the relationship between int and widening. And we're going to build those into the interfaces for int. Actually, no, this is more of, no, this is not actually built into the interfaces for int, but it is still something about the relationship. 2 integral and 2 widening invert each other. If you go round trip in this circle, you end up with the same value. So there's our circle diagram. Our interfaces using primitive trick express this by saying, yeah, if I apply that other function to my result, I get back to where I started. So that's just built into the interface here. We also need to say something about how things compare. We want the comparisons to work the same way. So here, we can just compare some numbers, or we can convert and then compare. We will get the same value for the Boolean result. That's our triangle diagram. And again, we can just build that into the interface for less than or equal on ints. So we've got the circle, we've got the triangle. There is one more we need. We need to know about increment. Oh, first I should say, we apply this, we have a triangle for any of the comparisons. You can always, comparing gives you the same answer as converting then comparing. And finally, for increment, the picture is a little more complicated. It's a square. And this is saying that it doesn't matter whether you convert then increment or increment then convert, you get the same answer. And we can just build that here into the interface of increment. Doesn't matter which way you go, you get the same answer. Yes?
What about UB? What about going off the end of your integer? Increment past the end? Like
So the question is, what about undefined behavior? So you still have to match the interface for increment on an integer here. Undefined behavior is handled by, the overflow is handled by other parts of the interface.
Okay.
But if you succeed, you'll get the square. And if you're not used to the circle, the triangle, the square here, that means you should learn a little bit of category theory. You don't have to learn a lot of category theory, but just a little category theory really will help you understand types better, and you'll get used to these pictures. Okay, we've got some tools. How do we write our proof? Well, actually, I'm going to do it the cheap way again. I'm just going to call a counting theorem, but I'm going to call a different counting theorem. I'm going to say we can count in ints because we can count in widening. What does that theorem look like? Well, it looks very similar here. In fact, if we put the two side by side, like they line up line for line. So we're going to call this, we have to meet its precondition. Why do we meet the precondition for the counting theorem on widening? Well, that precondition repeats not exactly the operation on the left side, but the operation inside the interface of the integer operation. So we are repeating something on the left side, and that interface said it gave the same result as the comparison on the left side. So the two comparisons are the results of the comparisons match. The branches, the claims, repeat each other. The direction of the claim repeats each other. So because the left-hand claim is true, the right-hand claim is true, just from reading the interfaces. That means that we can assume the post condition on the right, that we can assume that that loop's ends and all the claims in there end, because those are not our problem yet. So that loop is not a problem, and our loop repeats the events in that loop. Again, it looks like it repeats it very directly because it's the same syntax. But what's actually happening is every time we compare I to E, inside the interface for not equal, there's a comparison of widening. And it matches the comparison of xy to cd. And every time we compare I to E with the less than, it matches, or something in its interface matches the comparison on the right. And it gives the same, and it gives a matching result because that was the triangle rule. And the increment rule, every time we increment I on the left, inside that interface, there was a widening increment that matches the increment of xy. So the loop on the left is repeating literally every operation in the loop on the right. It's just doing more because those repetitions happened inside the interfaces of the operations on the left. And every branch on the left is repeating the branch on the right because those interfaces said the Boolean results were the same. And so we are just following the same pattern. The loop on the left runs for exactly the same length as the loop on the right, just by repetition. So there's another proof. Things do get harder. How do we do this? Shifting context again, new robot. Well, this is the part where we are ready to finally make our descent. We are going to write the template that generates these neighborhoods. Each of these neighborhoods is going to be a specialization of our template. But we also need some tools to express how the different widening types relate to the next ones down the road. down the slide, and how the individual bit types relate to bool. So for that, I'm going to use a set of axioms. This is what an axiom looks like. Very much like a theorem. The only difference is instead of saying claim implementation, I'm saying posit implementation. I'm saying we're just assuming this is true because the reason it is true can't actually be written in C++. This is a fundamental thing from our C++ point of view. There is a reason. The reason is in your compiler or in how your computer works or some combination of those. But the reason why this works isn't going to be in C++. But it's saying something very simple. It's saying that there is a reference result that we can calculate in C++, and in fact we will calculate it without doing a full width comparison of A, B, and C, D. And it's saying that, okay, the actual comparison we have gives the same answer as the reference result. The actual comparison will hopefully run faster than the reference one because, you know, tearing things down like this just slows us down. And computers have ways to make things fast by, say, using an using a comparison instruction that compares a whole lot of bits. But this is just an axiom that says, yeah, we know how to calculate that, and if the actual operation doesn't give the expected result, our computer is wrong. So what is that reference function? Before I get to the reference function, we're going to do the same thing for all the comparisons. So all of the reference axioms for comparisons just look alike. And here is the frame for reference less than or equal. It has 4 cases: bitless kind, unsigned bit kind, signed bit kind, and multiple bits. Get used to that pattern. You'll be seeing it a bunch. And for the first 3, we're just going to make a table. If we use less than or equal on 2 bitless integers, the answer is true because they're both 0. If it's 1-bit integers, the answer is true 3 times out of 4, and the table tells us which one is the 4th. Same thing, you know, one table for unsigned bits, 1 table for signed bits. And then finally, for the multiple bit case, we'll have a simple algorithm where we split the bits into 2 parts. And we look to see if the high digits are the same. If the high digits are different, we compare the high digits. Otherwise, we compare the low digits. And that's how we know whether one two-digit number is bigger than another. And you've probably seen this algorithm before sometime. I know I have, but, you know, again, familiar is not trivial. But it's not really that hard to write this, because you've seen it before. And the same thing applies to not equal and less. It's just the table is a little different, and we used a different comparison down below. So that's how all of our reference comparisons are going to work. We look, you know, for single bits or bitless, we look it up in a table. And if it's a multi-bit number, well, we ask, are the high digits the same? If they're not, compare the high digits. If they're the same, compare the low digits. So that's the reference functions for not equal, less, less equal. I know you know the drill by now. There's going to be one for increment. The interface looks a little different. Really, the only reason the interface looks a little different is that increment is an in-place operation. So I went ahead and wrote reference increment as an in-place operation. But what this is saying is, if you give me some widening number, well, I can make 2 copies. I reference increment one, I actual increment the other, and the axiom says those 2 operations give me the same result. So this is just saying that The real increment operator gives us the same result. It gives us the result we expect. And the reference one expresses what that expectation is. So, how does that one work? Well, again, the frame, bitless kind, unsigned bit kind, signed bit kind, multiple bits, divided by if const expr. I will put one more thing in here in the reference one. Right up here, we're going to say, no, you can't increment your maximum value. You will fail this assertion, and it's on the caller to deal with this. And you'll notice reference increment, and none of the reference functions have an interface. We're just leaving them out there in line where everybody can see them. The robot will walk through them because the robot only stops at interfaces. The robot sees interfaces. The robot does not go into implementations from an interface. So with that, when we know we're not at the maximum value, we can make our table. Yeah, you can't actually increment a bitless number ever. I probably shouldn't have said the return AB on that line. Oops. Yeah, you can't even do that. If you successfully increment an unsigned 1-bit number, the answer is 1, because you can't increment 1. But you can increment 0. Same thing, signed bit. If you successfully increment a signed bit number, if you passed that condition up above, the answer is 0. So there's our answers. And I should say I'm using 1-bit and 0 signed bit as they are just defined to produce, what is it, two unsigned bit of true, or two signed bit of false. So that's how they interact with 2-bit. Yes?
So you're not, your unsigned increments aren't wrapping around?
No. The widening types don't wrap around. They just stop. Yep. So, and that won't bother us. It'll, in fact, make our life a little easier. I wanted to get rid of that nastiness. Okay, multiple bit numbers. Okay, a little complicated, but I'm sure you've seen this before. What do? We look to see if the low digit is at its maximum value. Don't you wish like int had a dot max value? And if the low digit is not at its maximum value, then we increment the low digit and we leave the high digit the same. Put them together to get our result. If the low digit is at its maximum value, we increment the high digit and put that together with the minimum value of the low digit, which, because it's unsigned, will be 0. And that gives us our result. So a familiar way to do it, maybe the code looks a little wonky, but it fits on the slide. And that is the reference for how we increment a number. This is, if our compiler increments a number and gives us a different result than this, it's doing it wrong. So we now have our reference axioms. Let's get back to the problem. How do we fill this in? Bet you can guess right now. We first fill it in by saying we're going to split into 4 cases: bitless, unsigned bit, signed bit, or multi-bit. We will start with bitless. This proof's going to be short. We're going to call the reference not equal axiom. What that does is it makes our robot walk through the table here, but not the whole thing, because if const expr, it only walks through the bitless part. Walks through this, says, oh, not equals returning false. And more for our benefit than the robot's, we'll just put that here so we can see it. Not equal returns false, and the robot can check this because it just walked through the table. And if we take a look at our post condition, which I'm actually going to swap over to the other side here, the condition in our post condition repeats the condition in this claim. And the condition in this claim was, the comparison in this claim came out to be false. So that loop is going to end on its, before it's even run the body once. A little more complicated, the unsigned bit proof. This time we're going to start with an if statement, because it turns out when they're equal, it's going to be pretty easy. The hard part is when they're not equal. So we're going to put most of our effort into the hard part. Start by calling our reference less or equal axiom. Now, our precondition for the proof was that AB was less than or equal to CD. So our robot, walking through that table, realizes we are not in the upper right corner of the table. That is to say, AB is 0 or CD is 1. But then we're going to call the not equal axiom. And we know that not equal returns true because we're inside that if statement. So it's repeating what happened in the if statement. So not only do we know we're not in the upper right corner, but we know we're in a spot where not equal returns true. We're in the lower left corner of these tables, because the two tables are laid out the same way. And what next? Well, we're going to call the reference less axiom. And we know that we are in the lower left corner of this table. Less is going to produce true. We'll make a note of that. So this is what we know just by looking at the axioms about comparisons. We've figured out that when AB is not equal to CD, and because AB was less than or equal to CD, AB is 0, CD is 1, AB is less than CD. Moving on a bit, we'll call the reference increment axiom. And we'll do an increment ourselves. And we'll say, yeah, after that increment, we ended up at 1, because that's what the reference increment axiom told us. And if we compare 1 to CD, is 1 not equal to CD, which is also 1? No, it's not. That will produce false. That comes from the interface for not equal. So all of this, the robot can approve of our claims, and if we compare it to our post condition, then we see the first time we come to the loop condition, we're repeating that branch up at the top. Then we come to the claim that XY is less than CD, and that's just repeating this claim that AB is less than CD, because they're still substitutable for each other. When we increment, we're repeating this increment. The next time we come to the loop condition, we're repeating the comparison that is in this claim at the bottom. And that comparison, we know, produced false. We know that false makes branches go in a particular direction that gets us out of the loop. So our robot can walk through this and see this loop is just repeating events that happened inside the proof. And that's just generally true of how theorems go. The way the conclusion of the theorem is shown is that the conclusion of the theorem is just repeating things that happen in the proof of the theorem. And the way the proof takes advantage of the preconditions is that the theorem repeats the preconditions. And the way that the caller makes sure the preconditions are going to hold is that it sees that the preconditions repeat things that it already knows. So repetition is what drives all of this. Moving along, the signed bit case looks very similar. We're just running through a slightly different table. And when we look at what corner we end up in, it's the upper right corner where we're counting from -1 to 0. And when we increment -1, we get 0. And we can compare that to our post condition. Same deal. It's just like before. So now we get to the hard part, multi-bit numbers. How do we count from AB to CD? Well, you've probably seen this before too. First, we look at them as separate digits. We use split bits on both of them. And then we generate a whole lot of pairs of digits that happen in between A, B, and C, D. And we generate them, each column here, most of the columns anyway, are generated by incrementing y until y gets the maximum value. The last column is a little different. The last column we generate by incrementing y until it is equal to d. In between columns, what do? We increment x and we set y to its minimum value. So that's the scheme for counting from AB to CD. And we can write that as a bunch of loops here. So this is the frame for our proof. This is how we're generating the number of events that we need. But now we have 3 problems. We have to show why these loops end. What are we going to do? We're going to do the cheap thing now. Going to call the counting theorem, not recursively. We're calling the counting theorem on a smaller widening type. It's a different specialization of the counting theorem. So we're going to say, yes, we can count from, we're going to use this theorem to count from x to c. And that will make our loop that's coming up will repeat the loop that the counting theorem gave us. But there's a problem. Now we have to show that the precondition holds. How do we know the precondition holds? Yeah, we'll stick in a little code back here. Call the reference less or equal axiom. So that says, okay, there are 2 cases. Either A is not equal to C, in which case we know that A is less than or equal to C, which is what we're after at that point. Or A is equal to C. Helpful interface of less than or equal will surely tell us that if A is equal to C, we're comparing something against itself, the answer is true. So with that precondition is robot approved. And now we can do the same thing counting from y to its maximum value. This loop just repeats the things in that post condition. What about the claim here? Well, helpful interfaces come to the rescue again. Very helpful thing to put into the interface for less than or equal is that less than or equal the maximum value is gonna be true. So we'll just assume that's in our helpful interface. Okay, this one robot approved. Last one, how do we know we can get from y to d? Well, call the counting theorem. And we're just going to repeat that loop. But again, what happens here? Well, this one, excuse me. In this case, there is a way for the robot to figure it out because the robot knows you either went through the loop body or you didn't. If A was equal to C, didn't go through the loop body, in which case y is still equal to b, and we know that b is less than or equal to d because of the less or equal axiom. Otherwise, we went through the loop. Every iteration of the loop ends with setting y to the minimum value. That's the last thing we did before we exited the loop. So in that case, yeah, y's minimum value. Y and d have the same type. They have the same minimum value. It's a static member. So that gives us a bunch of robot-approved loops. We've improved this so that we know this code is fine. We just don't know how to get from this code to our post condition. So let's put our post condition over here again. How do we get from the code on the left, which our robot now approves, to the code on the right, which is doing some different operations? And to do this, excuse me, to do this, we're going to need to refactor a little bit. Here's a handy refactoring trick. We're going to pull out these bits where we increment stuff and put them in lambdas in order to give them a name. And then use the names instead of doing the operations directly. Just a refactoring trick here. What do you do next in this refactoring trick? Always. You add assertions to make sure you're using them at the right place. So we are only going to advance y, increment y, when y is not equal to its maximum value. When y is equal to its maximum value, we use it advance x instead. And there we increment x, set y to its minimum value. We're going to refactor a couple of comparisons to the comparisons on y. We are going to pull out and give names to using that same lambda trick and put in an assertion, because that's what you do next. We only compare against max when x is not equal to c. When x is equal to c, we compare y against d. So there's our refactoring. How do we take advantage of our refactoring? Well, I'm going to introduce a new variable back here, xy. And I'm going to start xy with ab so that xy is just x and y put together. And I'm going to keep it that way by changing the code where we increment x and y, where we modify x and y. Every time we call advance y, we also increment xy. Every time we call advance x, we also increment xy. And we call the reference increment axiom so that the robot can see we are keeping them in sync. Xy is always x and y put together. Once we've done that, we can now go into our comparisons. And every time we do a comparison against y, we are going to make a prediction about xy, whether xy is not equal to cd. On the left, when y is not the max, when we're comparing y against the maximum, well, we know that x is not equal to c on the left, and because of the reference not equal axiom, we know that that means xy is not going to be equal to cd. If the first digits are different, the numbers are different. When we're in that last column, when x is equal to c, we know that the comparison of xy to cd is going to come out the same as the comparison of y to d. When the first digits are the same, we compare the low digits. That's what the reference not equal axiom told us. So with that, we can come back to our loop and we can see each time we compare xy to cd, we're going to match something that happened in either y is not max for the first part of the counting, or y is not d when we're in that last part of the counting, because each one of those made a prediction about whether xy was not equal to cd. It performed that operation. And as long as we were comparing against max, it was just saying xy not equal to cd is going to be true. When we were in that last loop at the end, we were saying it's going to be the same condition. So these two loops are, the bottom loop on the left is going to end at a corresponding point as the loop on the right. And of course, every time we were going through, the increment of xy matched the increment that happened either in advance y or advance x, whichever one you hit next. Because we're just following along as we go, and our robot can just match this up, watching, match up events, looking for repetition, find the cycles, and say, yeah, that loop is just repeating the things on the left, except for that pit that I didn't color in where xy not equals CD. But we don't have to repeat that in, we've shown why the loop ends. That loop is always repeating things that happened in the body of the proof. So how do we get that last bit? How do we get xy less than CD? You know the drill by now. We're going to put in some comparisons that basically express the reason xy is going to be less than CD. Up at the top, it's going to be because x is less than c. Down at the bottom, it's going to be because y is less than d. Pull those out, refactor them using the lambda trick. Use the names. We can put assertions in, saying that we use them in the right place. And we can call the reference less axiom to make a prediction about whether xy is less than CD. And in fact, we're not just going to make a prediction, we're going to predict that it always gives the result as the comparison we just did, or the comparison we're about to do. So once again, we are sliding this code in there so that it can be repeated by our post condition. And when we come back to our post condition, we see, yes, xy less than CD was performed and gave the same answer as the call in each of these claims. And that is showing that everything in our post condition is just repeating things that happened in our proof, and all the branches are going in the same directions. So there we go. Proof that you can count. It's a very general sort of thing. Most, if you work at it, most loops can come down to counting, because Bertrand Meyer thought that was going to be good enough for all loops. In fact, he was just doing counting downward, not even counting upward. So the next time you're in code review, well, maybe not the next time, some future time when you're in code review and our languages have improved, and you're faced with this question, you'll have an answer. Yes, the loop ends because it repeats a series of local events that happened before the loop started. Each iteration consumes some events, and the events before the loop are eventually exhausted because there's some finite number of them that happened. And that has a couple of nice properties. One is it's local. This one satisfies our criteria for locality. And our robot can, it's not that hard to make our robot follow this, because our robot had to look for repetition just to understand code in general. You just have to add in cycle detection. I am hoping for one more property, and I don't know if I've really got it or not. But what I am hoping is that this is a practical way to express why a loop ends. Because I don't want it to be another 35 years before this becomes common practice. I think we can get to a point where we are putting the reasoning for our programs into our source, into the structure of our code, so that algorithms, so that robots can check our reasoning and tell us when we went wrong. So, stepping out a little bit, I want to take another look at these two categories: loops that end, loops that don't end. Kind of famously a fuzzy border in between them. This is not a sharp Boolean distinction the way you might think. It's an open-closed topological border where they get very close and you can't quite tell at the edges. That's really what the halting problem is about. And I'm going to say there's really a misconception that is driven by how we think not works. We like to think of not as like a nice, sharp Boolean division. There's X and there's not X, and that's supported by our understanding of finite stuff. But when we get to infinite things, the things that might run forever, I think there's something wrong with that. And if you will indulge me in a bit of mental gymnastics, a maneuver I call the reverse Karl Popper, the category on the top, loops that end, is a meaningful category. When I say that a loop ends, I can support that. That is, when we come to the loop, I could show you a finite number of branch decisions, a finite number of bits that are going to be repeated by branches in that loop that together ensure that the loop will end. That is a nice, that makes, that is a sense of meaningful here. It is a thing I could say and support. The bottom category isn't like that, not in the general case. I mean, there are some loops that repeat the same decisions over and over that you can show don't end. But in the general case, to show that a loop doesn't end, I would have to convey an infinite number of branch directions to you, an infinite number of bits. And I am unable to convey an infinite number of bits to you by speaking or any other method. I'm just not that fast a talker. And that means that's different. There is something meaningless about that bottom category. Not isn't symmetric when it doesn't create that nice Boolean symmetry when it comes to infinite things. And there is a computer science version of this. Recursively enumerable, the complement of recursively enumerable that's kind of useless. And I will say, yeah, it may be meaningless, but that thing on the bottom, saying that a loop doesn't end, that is nobody's precondition. No function depends on a loop not ending. Functions depend, there are lots of functions that depend on a loop ending. That can be a precondition for a function. It can be a postcondition you can establish in a function. That is a thing worth saying. The bottom one, not so much. There is, however, a related distinction that is sharp and Boolean. And that is this one, between loops that are required to end and loops that are not required to end. That is a Boolean choice that we make. We require or do not require. One choice that we can make about a loop. And we can convey, yes, we require this loop to end. No, we do not require that loop to end. In fact, we really should convey that. That's part of our intention when we're writing a program. We should have syntax that conveys that decision. And we can use, most loops we want to end, we'll use the simple syntax for that, but we could have a separate, more complicated syntax, especially for the rare cases where we want to write a loop that is not required to end. Because if we do that, we can have our robot help us with another distinction. The distinction between loops that are required to end and have a clearly explained local reason to end, and loops that are required to end but have no clearly explained local reason to end. Do we need another syntax for this middle category? No, we don't. We shouldn't be writing those. Because if we were requiring a loop to end in practice means requiring there to be a reason for it to end that can be expressed. If you don't have an expressible reason, then you don't know that your loop ends. And when I say an expressible reason, really expressing clearly, the gold standard for expressing clearly is so clearly that a robot could understand it. So with that, thank you for listening. Are there any questions? Yes.
So we had this conversation before, but I I always try to map your reasoning model to like a set theory reasoning model, because in the set model, you would look at the branches reducing the set of possible values between the start condition and the end condition, and you can see that it guides to convergence without necessarily having to branch through the iteration. I don't quite understand how in this reasoning model we can do that without actually branching through the entire iteration.
Okay. The phrasing was complicated, but I think the fundamental thing is how in this reasoning model do we do like a counting loop without actually having to test all possible inputs for the count, all possible start and end positions. And the answer is that's where breaking it down into neighborhoods really helps us. We prove it one step at a time. And okay, yes, for single bit numbers, for bitless numbers, we do try every possibility. But there aren't that many possibilities for them. That's not complicated. And then we use that to build up the theorem, setting that aside, setting that in another neighborhood so that we're not looking into it again, setting it behind an interface. We use that result to build up 2-bit numbers. And now we're not going through all the combinations. We're just saying, yeah, something happened to the high bit, something happened to the low bit, and we're not like looking at the individual values anymore. And then we go to 4-bit numbers, and 4-bit numbers are just as going from 2 to 4 is just as complicated as going from 1 to 2. Going to 8 is another step of just the same complexity, and we work our way up. And maybe we have a separate path where we handle the signed the things where we had a signed bit to deal with. And so yeah, we just build up, basically doubling the number of bits at each stage. At no point, by the way, do we have a theorem that says we can count from any integer to any integer. That was never expressed here. This is a theorem schema in the mathematical sense. There is no general theorem about integers. There are individual theorems about integers of a particular width.
So the recursion is on the size of the integer, not on the values of the integer.
Yes, the descent there, the recursive template expansion is on the width of the integer, not on the values of the integer there. And but I will say, if you actually run the proof, and like if you turn on all, running through all proofs rather than never doing the optimization thing of saying, yeah, we will just do our part and skip the proof below. If you turn on all of that, there is a lot of computation that goes on. That's because at that point you really are going down and branching on every bit. But we don't have to do, our robot doesn't have to do that because our robot is limited to a neighborhood. It's only if we turned on check literally everything at runtime, everything gets much slower. Yes?
No, one more question.
So I get to take one more question.
All right, I'll display my ignorance. Go back one slide, please.
Just one slide.
Okay. Well,
thank you for listening. You probably want to go here, maybe?
Yes. And the middle thing there. No clearly explained local reasoning yet. I am not a mathematician, but I think about loops like stood copy.
Mm-hmm.
Take 2 iterators.
Mm-hmm.
Advance iterators. There's no locally clearly explained reason end. As a matter of fact, that's a precondition for the loop.
The
end is reachable from beginning.
So Marshall brings up if you look at a standard algorithm like copy, it has a precondition of reachable.
Mm-hmm.
A precondition is in the neighborhood. So what's happening is the way you write that precondition is there's a loop in the prologue for the interface for copy or whatever. It is true that you can only really do that for forward iterators and up. But that's because reachable, as the standard defines it, for output iterators and input iterators is a bunch of mystical nonsense. It talks about something called the input or output, the sequence, and the sequence doesn't even exist.
Yes.
It is talking about angels dancing on the head of a pin. The answer for input iterators, or yeah, you don't want to use this answer for output iterators, it might be bad. No, you can. If you were writing yes, you would use this for output iterators. If you're looping to the end of an input iterator or an output iterator, you have no reason, use the things at the bottom. And that's why you can write yes. It's why you can write cat. All of those Unix utilities that have a loop that doesn't end for any reason inside the utility, you use the unbounded variance of the loop. So I guess that was the last question. So thank you again for listening, and I will be outside at the food area for a while.